Good afternoon or morning or whatever time it is. I wasn't feeling very well, so I wasn't sure if I was going to be here today. Here are your notes. This is the last day of notes before you have a test, which is coming up next Tuesday. And so Friday and Monday will be review days, and the review question numbers are already posted on the class website. I hope to get the pictures up soon, but problems are there. You can get started whenever you're ready. Tonight you have CP25, which is a few problems. So the last couple are pretty hard, so it'll take a little bit of time. And right now I want you to have your book out and be looking at page 353. So go ahead and get your book out and do a little bit of reading on page 353. Pause the video if you need to. So air navigation bearings are measured in degrees clockwise from north. And so if you were on an airplane, maybe we were traveling from Tucson over to Oregon somewhere, then we might say that we're flying very long way around here at a bearing of like 340 degrees. And so that's from north. And so we'd be flying all the way around, headed over to Oregon at a bearing of 340 degrees. Maybe that's a bad example. But your book uses that we're going at a bearing, flying at a bearing of like 225 degrees. And again, that's from north, where north would be 0 degrees, which is kind of a little different than how we've been doing angles in standard position. So bearing is what we're talking about today, and there's obviously these two different ways of talking about bearing. So this way, where they just give the degrees, that means degrees from north, clockwise. And the other way is when we're talking about surveying or water navigation, are given in terms of the acute angle that the path makes with a fixed north-south line. And so they had a few examples. And so you're going to be drawing little north, south, east, west, little directional compasses. And so we have something like this where this would maybe be the angle that's 35 degrees, and that's from the north-south line. So we would say that this was south 35 degrees towards the east. And this is, I think, probably the traditional way we think about bearing. And let's see, they have another example where we might say from the north-south line. So those are the main ones that we always start with north-south, and then how many degrees to the east or to the west. So this might be like, I don't know, 70 degrees. And so we would say this would be north, 70 degrees towards the west. So 70 degrees west, whatever it happens to be. And so there's a couple examples in there that you can look up.
Al just came to me to let me know that he found it out.
All right. So that's a good example one. A ship is 40 miles west and 15 miles south of port. The captain wants to sail directly to port. What bearing should be taken? Let's go ahead and pause the video if you need to copy down. All right, so first of all, we're talking about a ship here. So this is water navigation. And so I'm thinking that the bearing that we're looking for is like north or south, some sort of degrees, east or west. That's the sort of fill in the blank bearing we're going to be looking for. So always, we want to have a really good picture don't be shy. You don't have to save paper here. Make a big picture so that you can have proper labels, and see parallel lines is going to be really important for these problems. A ship is 40 miles west and 15 miles south of port. So I'm going to make a port here. So this is P for port. And then a ship is 40 miles to the west, so directly west, 40 miles, and 15 miles south. I guess I should use MI for miles. 15 miles south. So we're going to pretend that this is the ship right here, 15 miles to the south. And these must be at right angles then. If this is to the west and this is south, and that's a 90-degree angle. And so this is where the ship is right now. That's our ship. And we're trying to figure out this bearing that he needs to take to get back to port. So obviously what we have here, this was south. I'm going to S for ship here. I'm going to say ship. Okay. Was a north-south line here. And so there's this little directional compass that we can put on north-south. Never eat shredded wheat. Okay. No. And so we're trying to figure out what is this angle. That is really the question there. And if we can figure out that angle measure, then I know that my bearing on this path to port would be north so many degrees towards the east. And so we want to figure out how many degrees that is. And we have some information here. I think we can use a trig function here to figure that out. So if this is my angle that I'm interested in, this is the opposite side, and over here we have the adjacent side. And so opposite over adjacent is a tangent function. So I think I can think the tangent of my angle theta is 40 over 15. Again, yesterday on the worksheet that you guys had, you ran into unit problems. Make sure your units are the same. So you might need to convert if that comes up. And then if we're trying to solve for the angle, right now it's trapped inside a tangent function. So to get rid of it, we use an inverse function to cancel it out. So I'm going to take the tangent inverse of both sides. Tangent inverse of the tangent undoes itself, so I can get theta as the tangent inverse of 40 over 15, finding the angle. And you probably want to be in degree mode again, because since it's an application, radians are kind of not very helpful. So I do believe it's going to want things in degrees. So tangent inverse of 40 over 15 gives me 69.4 degrees. And so that's going to be a bearing of 69.4 degrees north, 69.4 degrees east for our ship's bearing. So make sure you got a good picture. Make sure you've got north-south lines in there, little directional compasses. And it's really important too, I think I'll mention this right now. Let's say I have a starting point here and another ending point here. And they each have this north, south, east, west, never eat shredded wheat, okay, compass passing through them. And what we want to understand is that if I were to connect these 2 points, what I have are lots and lots of parallel lines, okay? And so if you're looking at these, I have parallel lines. These north-south lines are parallel, cut by this blue transversal. And so I create, here is parallel line, transversal, parallel line. These angles are alternate interior angles, and therefore they're congruent. And this happens all over the place. We have east-west lines that are parallel to east-west lines. So I have a parallel line, transversal, parallel line. These little angles are also congruent. And this is going to happen over and over. So pay attention If you extend this line, corresponding angles are congruent. So this, let me extend this blue line in this direction as well. So this is where parallel lines came in. This is so important. Again, we have parallel lines, east-west lines. This corresponding angle is congruent to this corresponding angle. And of course, these are vertical angles, and they're also congruent. All of these things from geometry are going to come into play here. So know your parallel lines. They're really, really useful. All right, let's see. Example 2. Again, if you need to pause the video to copy down the question, feel free. All right, a ship leaves port at noon and heads due west at 20 knots per hour. Knots are just nautical miles per hour. At 2 p.m., the ship changes course to north 54 degrees west. Find the ship's bearing and distance from the port of departure. So again, I really need a really good picture. So we're going to use as much space as we need here. A ship leaves port. So here is the port. He leaves port at noon and heads due west. So if I'm drawing in my little navigation here, north, south, east, west, then the ship is traveling due west. So he's going to go due west at 20 knots per hour, 20 nautical miles per hour. They abbreviate nautical miles in nautical miles. At 2 p.m. So he started at noon, and then at 2 p.m. he changes course, which means he went at 20 knots per hour, 20 nautical miles per hour, and he did that for 2 hours. So hours cancels, 20 times 2 means that we went for 40 nautical miles. So we want a distance here, not a time, not a speed. We need distances. So make sure that your unit is a distance unit. And then it's going to change course. So because we're changing course, I'm going to give myself another little directional thing here. So I can see my parallel line. So north, south, east, west. Never eat shredded wheat. All right, so at this point, he's changing course to north 54 degrees west. North 54 degrees to the west means this is 54 degrees towards the west, and that is now his direction. I'm going to make it a little longer just so I have a nicer picture. Okay, and so now we're traveling in this direction. He changes course to north 54 degrees west, and we want to find his bearing and distance from the port of departure at 3 p.m. At 2 p.m., he changed course, and we want to know where he is at 3 p.m. I'm assuming he's still traveling at 20 nautical miles per hour, and so this is only for 1 hour. So he's going to go 20 nautical miles for 1 hour, which is just the 20 nautical miles. All right, and so what do we have to figure out? We want to know the ship's bearing and distance from the port of departure. So I need to find out how far away that ship is from the port of departure. So that's a straight distance. I need to find this distance. I'll call it D, I guess. And then I also need to find the bearing from the port of departure. So I need the bearing from here getting to this point, which means I need to figure out this angle measure right here, which again is going to be something north so many degrees towards the west. All right. When you do these, we really, really need to look for parallel lines and giant right triangles. And to find this large distance, I need another really large right triangle. So what I'm going to do is I have this nice horizontal line here. I think I'm going to extend this and drop an altitude, if you will. These are perpendicular. And now you can see this giant right triangle. That's going to be very useful for me. And I also see this smaller right triangle. I need a lot of information from this piece. So I'm going to start with this little small triangle. I know that this angle is 54 degrees, and so I want to figure out what this piece is. Well, north to west is a 90-degree angle, so 90 minus 54. I don't feel well enough to do math in my head, so 90 minus 54 is 36 degrees. So this is a little 36-degree angle. And in order to find this distance, I need to know some side lengths. So I would like to find this side length right here. That's going to give me the total length of this triangle leg that I'll need. So I'm going to find x. I have an angle. I have this 20 nautical mile side, and x. That's going to be adjacent and hypotenuse. So I can write cosine. Cosine of my 36-degree angle is adjacent over hypotenuse. And just multiply by 20. 20 times the cosine of 36 degrees is 16.18, I guess I'll use. So x equals 16.18 nautical miles is our unit. 16.18 nautical miles. Okay. Let's see. I think I also need to find, I'm also going to have to find this length here. Because looking at this giant green triangle, I need to know this green angle measure, which I can get if I know this angle. So I need two side lengths. So I need this little side and another side in order to do that. So again, I'm going to figure out, I'm going to find this side, I'm going to call it y, and I can still use this little triangle right here that's sort of overlapping. So that would be my opposite and hypotenuse. So I'm going to write a sine function. Sine of my 36-degree angle is opposite over hypotenuse. So I can multiply by 20. 20 sine of 36. And I get 11.76, I guess I'll use. So y equals 11.76 nautical miles. Okay. All right, so now I have a total length of this leg. This 16.18 nautical miles and the 40 nautical miles, and I can get the total length of this leg. I'm just going to redraw this big green triangle so you can see it really clearly. So this leg was, the lights just shut down, 11.76 nautical miles. And that base is 16.18 plus 40, which I probably could have done in my head, but 56.18. And that's going to allow me to figure out this angle, which is right here. All right. I'll call this theta. And so I have opposite over adjacent, so that's a tangent function. So tangent of theta would be 11.76 over 56.18. And to free that angle measure, we're going to do tangent inverse of both sides. Tangent inverse and tangent cancel out, so that I get theta equals tangent inverse of 11.76 over 56.18. Type that into my calculator. Tangent inverse of 11.76 over 56.18. And I get 11.8 degrees. So this is 11.8 degrees, which is the same as this, 11.8 degrees. And that's going to allow me to find this, which again, this created a 90-degree angle. So 90 minus that 11.8 degrees is 78.2 degrees. 78.2 degrees. So that is this angle right there, the question mark. That's our bearing. North, 78.2 degrees towards the west. Very good. And then the last thing that we have to figure out is the length of this side, which if we have a right triangle, we could use the Pythagorean theorem, but I think trig is going to be easier. Excuse me. So using this triangle, I want to find D. Can use the same triangle, and since I know it's 11.8 degree angle, I can find D pretty easily. I have my choice of sides really, but I'm just going to use this one. The adjacent side and our hypotenuse. So that's going to be cosine. Cosine of 11.8 degrees is adjacent 56.18 over that distance D we're looking for. I would multiply by D and then divide by the cosine of 11.8. So 56.18 divided by the cosine of 11.8 degrees. Let's see what that is. So 56.18 divided by the cosine of 11.8. And I get a distance of 57.39, which I'm just going to round up to 4. So a distance of 57.4 nautical miles. A bearing of north 78.2 degrees west, and a distance of 57.4 nautical miles from port. So again, the really big thing here is really to draw lines so that you create right triangles. And if you can create right triangles that maybe overlap, then we can use little bits of information to find the bigger picture. Okay. All right. Have fun.